Today we are going to see the final classifier of our unit, that is actually neural network classifier. We have already seen many other classifiers like logistic, nearest neighbor, SVM, Bayesian, decision trees, random forest, and so on. This is the ultimate classifier, the start of deep learning, where we go as deep as possible to find what is the most crucial parameter in doing the classification task. In doing the classification task. That's what is actually the neural network classifier. The basic of neural network classifier will be seeing here, where we'll be understanding what is the core part that is making the difference between the normal machine learning and this neural network classifier. Right, this is also a supervised learning, but how it is actually different and how we are actually getting that much higher percentage of accuracy in neural network is, it is actually, we can say that neural network as a mimic of human brain actually. We have in biological sense, we know that our brain is actually a neural network pattern which actually do the operations how we are actually memorizing, how we are actually visualizing a particular object, how we are actually remembering a particular person, how we are actually doing a particular job. Everything is actually facilitated by our brain through some neural network pattern. Why those neural network cannot be made artificial, so that is actually the thing came, and finally we named something called as artificial neural network that can make some huge classifications very easy. Say for example a video classification, or an image classification, or an audio classification, or any other signal processing task which are very high or very huge for a normal machine learning thing, can be done very easily by using some neural network classifications and the higher versions, what you call as recurrent neural networks, convolutional neural networks, and so on. Right? We also have many activation functions which make this neural network pattern to grow as high as possible and excel in its accuracy and other metrics. Now, the basic definition, what we can call for neural networks is, neural networks mimics the human brain by learning from the training set. So here also we have the training data available. So by this itself you understood that it is also going to be supervised. So from learning from a training data set and applying the learning as well as the experience to generalize patterns. So we know what is generalizations. Generalization is nothing but how my model is actually behaving with respect to an unseen pattern. We have something like which is already seen, so that is actually coming in training. When I show an input which is actually not seen by my model, how it is actually predicting the output, how it is actually behaving, is actually called as the generalizing. It is actually understanding from training and generalizing it to some output pattern which is not already seen. So that is actually the neural network pattern. The most important thing over in neural networks is, in neural networks there is an feature which is I can say both an advantage as well as a disadvantage. In neural networks, the model features are auto-generated. Say for example, if I say an image processing algorithm. Hope many of you guys have already done image processing in your earlier projects in predictive analytics as well as now hackathons. The most important stuff over here in image processing is in machine learning algorithms, say for example SIFT or SURF or PCA or some algorithms, we will be stating what will be the feature of the particular algorithm, what will be the feature of the particular image, we'll be giving it. Say for example, scale invariant key point features, or surf speeded up robust transforms, or will make some transformation over an image, and we will give that as a key feature of that particular image. We will state what is the feature. But the important thing about the deep learning concept is, here the features are auto generated in something called as a hidden layer. We have something which is actually hidden from the model developer, and the features are learned automatically. But I can have an action over that hidden layer by using some activation functions, but that is an external stimuli what I can give to the hidden layers. But internally, it is actually automated by many non-linear patterns. Some say that it is a very good advantage. Why? Because when I go for a very high level image processing task, say for example film editing, when you go for any animation film editing, or when you go for any realistic film editing, so for those cases we need to process an image, video, audio, and all the multidimensional data in a particular instant. So what you have to do, you don't know what is the essential feature you have to keep on. So for those cases, we have to rely only on deep learning, which can make the features auto-generated and it can work on that. So this is actually the thing. But the main disadvantage here is the developer by himself doesn't know how the model is actually doing that particular classification. If it is a machine learning kind of stuff, we can easily say that the distance between these 2 points is equal to this much. So we say that this point is classified as red or black. I can reason why the point is being classified as red or black. But in neural networks or in deep learning patterns, I cannot able to reason that this particular classification, as this particular object is classified as a male object or a female object, I cannot able to reason that because of this feature only it is actually being classified, because the feature is actually hidden from me, right? So that is actually the both we can call it as an advantage as well as a disadvantage. Most importantly, we can call the basic unit of artificial neural network, I can call it as perceptron. So this perceptron, I can call it as a basic artificial neural network pattern, which actually tries to mimic an human being brain. We cannot directly make a robot which is actually behaving exactly as a brain of a human being, which is not available in real world as for now. You can see something like Indran or any Avengers or some other things which is actually available in movies but not available in real world. We have many robots like Sophia robot. Many other robots are available, but they are not a strong AI robot. They are weak AIs. Even Alexa is available. Alexa cannot do all the tasks. An AI is a thing which can do any task a human being can do. If I train a human being to do something, he will immediately do it. But that is not possible for a robot. Why? Because I need to train its backend also, and I need to make that particular robot to do that particular task. So still now we know that in this world there is no strong AI available. Everything is actually weak AI or medium strong. We can say like an AI. No strong AI is still available, right? So this is actually we not cannot exactly mimic human being. We can make it somewhat possible, right? That is actually the case. Let us first understand the structure of this artificial neural network. That ANN is a network of interconnected neurons. These neurons can be, say, for example, inputs or a hidden layer or an outputs and so on. We can understand how that neurons are being going to be interconnected and so on. Inspired from biological nervous system. So this is because of this biological nervous system only the brain actually functions. So that is actually being mimicked in artificial neural network, shortly called as ANN. So let us see how that pattern actually looks. Let me take this epic pen. Yes, let me suppose it will have some input layer, say IP. An input layer is available. I can have several inputs over here, say X1. I can have X2, X3, and so on. I can have several number of inputs, and these inputs are actually available as some data set, a training or a testing set, whether it's going to be a normal text pattern or an image pattern. I say, right? I have this. And using this, what I will actually do, usually like a ML kind, I'll be assigning some weights over these inputs to say how these inputs are going to contribute for getting the output. I'll be having something called weights. And these weights need to be predicted. We cannot predict the weights directly. We need to make the weights predicted. We need to calculate the weights. Right? So I'll have x1, x2, x3, x1. And for each of those, I'll be having the corresponding weights. W1, W2, W3, and so on. and for x1 I'll be having w1. Now, so far this is actually an ML kind here. There is nothing more different. In ML also we'll be having the weights and we'll be predicting the weights. After this, what will actually happen is we'll be having a summarization unit. I need to summarize everything, and for based on this summarization unit, I need to produce some result. This is what actually available in normal machine learning also. So let us see how the summarization unit is going to function here. Let me write it like a summation. So the inputs will be given to the corresponding weight. Will be given, each input will be given the corresponding weight, and they all will be summated. The weighted summation of each input will be taken, and those will be forming a hypothesis formula, and that will contribute to a particular output in machine learning. But in ANN, after some summarization unit, we know that these weights are being calculated through some hidden layers. In machine learning task, these weights are calculated through some normal layers, which is visible for the developer. But in case of a deep learning kind or a neural network kind, this hidden the weights are calculated from a hidden layer point of view. So we will be getting only the summation. So what we can actually do is I can actually give this summation result to something called an threshold unit. I can say that some threshold is available, and for this threshold unit, I can give these summated weights. And this threshold unit, what I call as the activation function. I call this as an activation function. Let me name it. This is actually the threshold unit. So far we have seen the input unit, the weighted unit, the summation unit, and the threshold unit. Finally, after doing the activation, what I can get is I can go further to get an output unit, that is an output layer. I can finally get the output. So this activation has a wide role to play here. We will see what are the different activation functions available and how each activation function is going to model the particular input. And what is the use of the activation function? If the activation function is not available, what will happen? Everything we can actually model and see. So this actually I call as a basic structure of an artificial neural network, which consists of an input layer, a weighted layer, a summation unit, a threshold unit, and the output. Right. So if I name it going to be a particular kind of thing, for example, if it is not going to have the same pattern, how this threshold unit can be understood and how the basic perceptron formula or basic perceptron hypothesis can be understood. Let us see that. If I want to state, for example, I want to state the summation. I can state the summation as sum is equal to. This is actually a weighted summation over all the inputs, and so I can say it as x star w. I can say it as x star w. So which can be stated as x1 into w1 plus x2 into w2 and so on. I can have up to xn into wn plus dot dot plus xn into wn. I can have those actually the weights. So on the whole, what I can say, this summation is going to be just summation. I can say it is going to run from a limit of I, say I equal to 1 to n xi wi, a normal summation unit. And this summation unit will directly go for output when it is going to be a machine learning task. But when coming to an artificial neural network task, this summation will get substituted over an activation function. So what will actually have? I'll be having some output. Say this is going to be my output. So how my output is going to be obtained is I'll be applying some activation function over here. Say for example, I'll be having like some as a function, say pi. I'll be having some function, say pi. And this pi actually I call it as a thresholding unit or an activation function. This pi actually I call it as an activation function. And these activation functions can be a stimuli between the input layer and an output layer. So how my input can be varied accordingly to get wide variety of output layers. If my model is actually doing the same kind of classifications only, I need to make it learn in a different way. Hope then I can actually change my activation function so that it can learn something differently. It can reduce the errors which it has caused previously. Those kind of steps. We will learn how we are going with this activation function is going to function with respect to feed forward layer, feed backward layer. Everything will be understanding point by point, right? So I'll be repeating what we have seen so far. We have seen the neural network classifier, wherein it is actually a mimic or a replication of a human brain structure, where several neurons will be colliding to do a particular task. When we'll be actually using this, we'll not actually use it for a normal kind of classification task. When the classification is going to be huge or a complex classification task is going to be involved, then I need support from neural networks because they can do something which is actually complex. So I take those neural networks, how they actually behave, and what is the main feature there. They model features are actually auto-generated and hidden from the developer. The developer cannot see it. So I'll be having an input layer, a weight layer, and these input and weight will collide to a summation unit where I'll be applying some activation function in form of a thresholding unit, which finally will give an output. Right. So this thresholding unit I call it as pi, and modeling this appropriate pi is also a major task. We have several varieties of activation functions, and choosing the best activation function is also an hyperparameter. Right. Right. Shall I go to the next slide? Can you take screenshot if needed? It will be useful. So let us see the basic structure of a neural network in terms of input layer, hidden layer, and output layer. Now we have this structure. What we have seen before is the layer in which the machine learning is there, and how machine learning differs from deep learning through an activation thresholding unit. Now let us see the input layer, the hidden layer, and the output layer structure. We'll have something like an input layer, hidden layer. Usually, hidden layer will be a non-linear pattern so that it can be as complex as possible. But if you increase the hidden layer to a very large thing, then what will happen is your model complexity will increase. And the time, the responsiveness of the model will also reduce. So the hidden layer will be there, and finally I'll be having the output layer. Yes. Say for example, I have a set of inputs. Say input one, input two, input three, dot dot dot. I'll be having some I varieties of input. I put some dot. Then I'll be having some input details in hidden layer where these input will actually collide with one another. So input one will be combined with two and so on. I'll be having those input layers here. Any input layer functions will also form. So I'll be having those one, two, three, and the inputs which are having less significance can also be biased, and so that their influence can be reduced. So everything can happen here. So I name it J. It will not go up to I. It may not go. So I reduce it to some J. And over here I can have several input layer, hidden layers. Here I have two input layers, say again. So I have the input layers and output layers ready. Now how they all will collide will actually the main matter over here. So let us see how they are actually going to be. I'm having some input layer. See, it will be actually an interconnection of several neurons. So these kind of interconnections we can actually see, and for each interconnection, I can also form the weights. So how the weights are actually being distributed? What is the weight for one W12, W23, and so on, W2J, and this is how the weights will be distributed. Usually a non-linear pattern. And if I wanted to make it linear, whether a non-linear function to linear or whether a linear function to non-linear, if I want to do anything, those transforms, I can use the activation function, which can convert a linear to a non-linear or a non-linear to linear also. Say for example, so what is this is? This is actually the weight of W11. I can say it is W11. If I say this is Wij. So every link, every interconnection will be supported by the corresponding weights, saying the significance of that particular connection. This is, say, example, this is W21, and say this is Wi3, and so on. Every interconnection will be a weighted sum so that it will say what is the significance of that particular connection. Then I can also have interconnection between the hidden layers to make it very clear that if my hidden layer is having more interconnection, it means that it is going to do a wide variety of prediction in a non-linear pattern. So this hidden layer actually makes your model understand what is the essential feature. If you reduce this hidden layer, then what will happen is the model may not learn more deeply. If you increase, it will learn more deeply, but the complexity of the model will also increase. So there should be a threshold, or there should be a trade-off between how many hidden layers should be there and how well your accuracy is secured. So they also will be interconnected. So in order to make it somewhat less, not drawing more number of interconnections, you can have any number of interconnections also. Say this can be connected to this also, and so on. Right? Finally, what will happen by these interconnections? I may have some activations over these interconnections also. So usually this is non-linear. I can say it is as non-linear pattern. This hidden layer surely will be a non-linear pattern. Why? Because only if it is non-linear, it can go as deep as possible and understand each of the every small nuances inside the data set. Finally, I'll be getting some output. Say output one. How many outputs you want, you can get. We have several classifiers like SPM classifier or a softmax classifier, everything, which can actually give as many number of inputs you actually require. If you require n inputs, you can have n output layers. If you require only one in output, you can have one output layer and so on. Right? Finally, I'll be getting the outputs. So this I call the structure of the artificial neural network, which will have an input layer, an hidden layer, and an output layer. Right? This fully I call it as an input. This is ranging from x1 to xi. My inputs, and this is the hidden layer, and this O1 to ON we call it as an output layer, right? And my full hidden layer will be a non-linear stuff which will actually make my model to predict or learn as deep as possible, right? I can increase the hidden layers and it is an hyperparameter to me. As long as I want, I can increase my hidden layer and do the things, right? So essentially used for a very good classification or a very big predictions in a very complex model, I can use this neural network stuff and do my task very easily, right? Usually, a normal machine learning algorithm cannot learn as deep as possible and give that much good predictions. But when I use a neural network model, I can get those kind of good network patterns, and I can get good results also. Yes. Shall I go to the next one? Now let us see the main part over here. Now we saw that so far the difference between a normal neural network classifier and the machine learning classifier is the activation threshold. So what is the role of that activation threshold? Why it is actually important? And if the activation threshold is not available, then how the neural network will behave? Everything we will see. And along with that, what are the different types of activation functions available and how they will make the input layer to give appropriate outputs. Now we will see those kind of steps. Activation functions in ANN. We have something called as kernel in support vector machines. That is also one form of thresholding, which makes a linear pattern to a higher dimensional pattern. So this ANN is also going to be like that, where instead of increasing only to a higher dimensional thing, it is going to act on the input layer and give appropriate output. Right? Let us see the basic definition of ANN, activation function. So activation function in ANN is an internal state of the neuron. By neuron, I mean the input nodes. So, what are the nodes available? Internal state of the neuron. It is used to convert the input signal on node of a particular ANN structure to an output signal. So, I'll be building a very big ANN structure. That ANN structure may have any number of input layers, any number of hidden layers, and they can have an appropriate output layer also. How my input should be collated in such a way that it should be acted on upon in the hidden layer and give an appropriate output. How it should actually function. Or, for example, if my input should be going in a different fashion, I'm giving bias to one type of classification alone. Everything I can actually make by using that particular activation function, right? So another important point over here is they introduce non-linear characteristics or non-linear properties to my neural network, to the network. If the network is actually linear alone, it can actually make it non-linear. So this is actually an activation functions role. Most important thing, if you actually omit this activation function, then what will happen is your model may fail to generalize when I go for higher level classification task. Higher level classification task, by what I mean is if you go for a very big video processing or some stuff related to that, surely your model may fail to generalize. The main thing why we are going into neural network is it can generalize when it going for higher level task. If it failed to generalize, then there is no use of it, right? So that is actually the thing. So now, so far you can see that this activation function plays a heroic role in neural network itself, right? Right. Let us see what is be happening if my there is no activation function available. So without activation function, what the model will actually do is the model will fail to generalize. It will not generalize well without activation function. Trying to change the color. The output signal, what is being generated? The output signal would be simple linear function. As we all know, simple linear function will be useful when you do a small number of tasks, small simple classification or simple predictions. If you want to do simple linear function is more than enough. But when you do a very complex task, say for example image processing or video processing, surely this simple linear function will not help, right? For say even for our ESPN cricket for data, simple linear didn't work and we went for a polynomial function, right? So those things are also we can keep in mind. So this linear function will not help us. So surely we need to go for non-linearity. And but the advantage is if you didn't use activation function, your output will be a linear function. So you can the advantage is output is easy to solve, but limited processing capacity only will be there. The is only visible in learning complex tasks. It will not process more. Only limited things will be available. Cannot be useful for complex tasks like image, video, audio, and other multi-dimensional data. So even if it is a very single dimensional data, I can go with a linear function. Here's I need to go for a polynomial function or some higher degree function, right? So this is actually that basic definition I can say about the artificial neural networks activation function, ANN's activation function. Let us see what are the types are actually being available here, right? Types of activation function. What are the types actually available is the first one. We can see that the very basic one called as identity function. The identity function is a very basic activation function, not useful for complex tasks. I see we seen that the activation function that should not increase the complexity of the output function. Then what we have to use is this identity function that says that f of x is equal to x. What is the input that will be given as output? There is no modification for all x. That is f of x. I'll be giving the same thing. So what is ultimately over here is it is a linear function and output is same as input. There is nothing more. Output, what is the output? That will be the input also. Output is same as input. So if I want to draw the pattern for this, we can draw like the pattern of this will be like a straight line going on. You can draw a straight line as much as possible. So this is actually an activation function with identity notation. But what is x will be y also. So it will be like a straight line following through an origin or a particular value. Where what is x, the corresponding y will be there. It will be a straight line across 90-degree tangent value, right? So let us go for the other types of functions. Second one is binary step function. Binary step function, as you see, the name itself says it is going to be used for a classification with binary labels, say 0, 1, true, false kind of thing, used in single layer networks. This layer will be classified either as 0 or 1 only, right? Single layer networks to convert the input to output. So what will be the case over here is if I say f of x can be equal to f of x can be either 1 or 0. F of x will be 1 if x is greater than some threshold, say c. If x is greater than t. If x is greater than t, or I can say greater than or equal to t. F is greater than or equal to t. And 0 otherwise, if x is less than t. So what is the t? T is going to be an hyperparameter again. That is a threshold. What I have to model by using my algorithm, right? X is t is going to be my threshold. So what is this? This t is going to be my thresholding function, which actually makes my model to generate whether it is going to be classified as either 0 or 1. A binary step function. Right? This activation function will make this t value to be computed and it will be used. Right? This is actually the thresholding function. And if you see the diagrammatic notation of this, how it will actually look is, say I have the x and y axis. It will be either a 0 or 1 step function. As I say, it is going to be a step function. Say it is going to be like a binary step 0, 1, 0, 1 like that, or any other particular area. It is going to be a step function. No negative values allowed, only 0 or 1 allowed. Third, we see a sigmoid function, the most famous classifier used in both the logistic classification functions also. the sigmoid function, and usually used in back propagation networks. We are yet to see what is back propagation, what is feed forward, and those kind of steps. The back propagation networks ranges between 0 and 1. The value actually ranges between 0 and 1, and the function actually takes the sigmoid curve notation. F of x is equal to, it actually takes the sigmoidal curve formula, that is 1 divided by 1 plus e power minus 2x. 1 divided by 1 plus e power minus x. So this is actually a sigmoidal function, 1 divided by 1 plus e power minus x, that can either take the value of either 0 or 1. Should see the diagrammatic notation of this, say x and y. The important thing to understand is we know the sigmoidal curve will be like an S curve, but the thing is it will not go to the negative quadrant. It will be in the positive quadrant only. So this is an S. It will be like an S, right? Finally, we'll be going and see the penultimate thing, that is hyperbolic tangent. Hyperbolic tangent function, usually used in optimization problems. Used in optimization problems, ranges between minus 1 and plus 1. So this is actually the difference between a sigmoid and a hyperbolic tangent. So it is actually ranging between minus 1 to 1, whereas sigmoid is going to range between minus 0 to 1. So that is the difference between hyperbolic tangent and sigmoid activation function. This f of x will be 1 divided by 1 plus e power minus x is with respect to the sigmoidal function, where here it is going to be just the same thing, where the hyperbolic tangent will be behaving. That is 1 divided 1 minus e power minus 2x divided by 1 plus e power minus 2x. One divided by 1 minus e power minus 2x divided by 1 plus e power minus 2x. So the curve also will be like the same as sigmoidal thing, but the only difference is it can also pass to the negative quadrant. It is the third quadrant also it can actually pass through, say y axis and x. It actually passes an S curve over an origin. So this is actually how the tangent function behaves, right? The final activation function is the ramp function. So ramp function is actually widely used, and this ramp function is actually remodeled into several varieties of activation functions like ReLU and so on. Let us see how the ramp function is going to behave. I take the paint in those pen. Ramp function is popularly called as Rn function. That is, R of n will be equal to x provided x is greater than or equal to 0. If x, it will be x provided x is greater than or equal to 0. So this is actually the function. The difference between this and the earlier thing what we have seen for binary step function is binary step function can be labeled it as either 1 or 0, but it is actually giving the same output as x is itself if it is actually greater than or equal to 0. It will not allow the input to be less than 0 else. So if it is less than, then it can actually give it as 0 as x is less than 0. So this is actually the ramp function. And the curve for ramp function, you can see it is going to be simply like identity function where the negative quadrant will not be available. So the curve for the ramp function will be They'll be having like this x and y. So if it is greater than or equal to 0, I'll be getting the same input as output. Else I'll be getting a 0. So the ramp function will be giving me only the positive quadrant. The negative quadrant is actually not available. Only the positive quadrant is available. So these are the 5 basic activation functions available in artificial neural networks. So you understand how these activation functions are available, which is linear, which is non-linear, which is binary, which can range from 0 to 1, which can range from -1 to +1, and so on. So that when you understand those kind of stuff, you can simply do which activation function I have to use for this particular classification problem. You can understand those steps, right? I am making it clear the basic introduction of neural network. I'll be giving a small recap from first. So what is neural networks in general is it is actually a basic gimmick or a mimic of a human brain where it needs to do a complex classification or prediction task very easily. It will. What is the main thing over here is the thresholding unit. What is the other name? What is the other name?
Activation function.
Yes, I can call it as an activation function that mainly separates the machine learning to a neural network deep learning kind. So in ANN, what I can actually have, I can have set of input, I can have set of hidden layers and output layers. My hidden layers is usually a non-linear term. To understand these things, so when you go for MCQ kind, you can easily understand how what is a threshold unit is an activation function. How is the hidden layer being correlated? Hidden layer is always going to be a non-linear stuff. That is also an important point. Hidden layer is always going to be a non-linear stuff, and if I want it to be behaving in somewhat different pattern, like converting non-linear to linear or some other thing, I can use something like an activation function, say identity function or ramp function, which are actually linear functions. Identity and ramp are linear functions, right? I can also go for a binary step or step function, which is actually giving for either a single layer network. For single layer network, if I ask you what a function is actually required, I can say it is going to be a binary step function. And if I ask what is the range of sigmoid function, you can say it is 0 to 1, and the range of hyperbolic tangent, say -1 to 1, and so on. So these things you need to keep in mind, and these diagrams also. So when we go for any classification task and we ask for this particular notation of this particular functions, we can easily say, yes, for this particular classification scenario, this particular activation function is needed. So those things we need to keep in mind. If you didn't use those activation functions, what will actually happen is your model will not be useful for this higher level image or video processing task. It can be used for normal data processing, but if you want to do a complex task, then the model will not support. You have to use those activation functions to make it non-linear or a polynomial kind of, right? Is the basics of neural networks clear? We are going to see it in the practical also for a particular classification scenario, right? What is neural networks? How the neural network structure will be there? What is activation function? And without
Yes,
activation function, what will happen? And what are the types of activation functions? Everything, right?